Well, welcome to Sci 118. This is sort of unfortunate circumstances for our class that we had our schedule interrupted by this nasty weather, but it happens. And I think I mentioned in class that I'm kind of expecting this winter to be to have quite a lot of storms. I just kind of have this feeling. And so I don't really want to fall behind. To fall behind right here at the beginning of the semester is not a good way to start the semester. So I'm recording this for you. This is going to be all about Chapter 3, our chapter about gravity, so that we can keep on schedule for Wednesday. We have to do our lab on Wednesday, which I send information to you about that. So I hope you got that information. So on Wednesday, we will meet at 6:30 in the planetarium to do the lab that we were originally scheduled on Monday. And then we'll do the lecture as well, or at least a lecture on one of the next chapter, Chapter 4, after the lab. And so hopefully we can keep everything on schedule at that point. So I will see you on Wednesday. But in the meantime, here is Chapter 3, which is all about orbits and gravity. And it continues the conversation we were having during our first session. We were talking about the history of astronomy, and at this point, we reached this point where we have two competing models for the solar system. The old model that Aristotle and Ptolemy came up with that has the Earth at the center of the solar system. But then comes along people like Copernicus and Galileo, and they're arguing that the heliocentric version of the solar system really is the correct one. They want to move the sun to its proper place in the middle of the solar system and having everything orbit around it. But there are some problems with the heliocentric model, as we talked about. It gets rid of some of the epicycles that kind of plague the Ptolemaic model, the geocentric model. But it's maybe it's a little bit more accurate, but it's not that much more accurate than the old model. And you're also lacking the parallax we talked about, the parallax measurements, where if the Earth is moving, you'd see some shifts in the positions of stars. And it was very clear that was not the case. No one could measure those shifts. Unfortunately, they didn't have the equipment that they needed in order to do that. So here we are at this point. We have these two models, and we just need more information here in order to figure out which one is the correct one. And the solution comes with some more information, and a lot of this data that we need is coming from another astronomer named Tycho Brahe. And he is born in the late 16th century, and he is considered the last great pre-telescopic observer. When he's doing his work, telescopes don't exist yet. Galileo has not turned a telescope on the nighttime sky quite yet. But he is able, using the instruments that he did have, to make some very, very accurate observations, and over a long period of time. So he's got decades worth of data, and he finds that indeed, even with all the epicycles have been added to the geocentric model, it still doesn't quite do a great job. His observations don't fit with what the predictions that the geocentric model is giving him. So he's very unhappy about that. And so he proposes his own model, which turns out is a little bit odd. It's a hybrid model of the solar system. And so, he knows there's no parallax measurements, so he's got the Earth at the center of this model. And so here you see Tycho's model with the Earth at the center. The moon is orbiting around the Earth. And so this explains the lack of parallax that no one can measure at this point. But he knows that, or he has this idea that really the planets are orbiting the sun, not the Earth. And so he has all the major planets orbiting around the sun, and then he sets the sun in orbit around the Earth. And so it's kind of this hybrid model where the planets are orbiting around the sun, but then everything is orbiting around or in turn, orbiting around the Earth. And so this is rather, at least from our point of view today, this seems a rather odd model, but he thought this was a good idea. And he needs some help with all this data. He's got, as I said, he's got decades worth of data here, and so he needs some help. Well, he hooks up with this guy Johannes Kepler, very skilled mathematician, and he meets him, and Tycho is very protective of his data that he has. And he's also very prideful about his model. He thinks that he's on the right track and he's going to become famous. So he needs help, but he doesn't want Kepler to kind of scoop him to steal all his glory. So what he does is he gives Johannes Kepler the hardest problem, which is the orbit of Mars. So he takes all his Mars data, the positions of Mars that he's recorded, and he gives all of that to Johannes Kepler. And he figures that Kepler is smart enough to solve this. But in the meantime, while he's tangled up doing this, Tycho will go on and analyze the other data and perfect his model of the solar system and get all the fame. And Johannes Kepler will kind of help him do that. And when Kepler gets this information, it's very, for the time, it's very accurate positions of the planets that no one else has. And so he looks at this, and he is just not able to explain the motion of Mars using circular orbits and uniform motion. Remember, both of these items are part of what Aristotle thought about the solar system, about the universe, is that the heavens are perfect and everything is in a circle and everything moves in a uniform way. And so he makes this proposal that he's going to abandon circular orbits. He's going to abandon this idea of uniform motion, which is a very controversial thing at this time. This idea is over 1,000 years old, and here he is proposing that we have to throw it out. So a very controversial idea. I have a little NASA video here, which hopefully will play back smoothly, and this explains this whole sort of concept about what was happening here with Johannes Kepler and Tycho Brahe.
The planets orbit the Sun in a counterclockwise direction as viewed from above the Sun's north pole. And the planets' orbits all are aligned to what astronomers call the ecliptic plane. The story of our greater understanding of planetary motion could not be told if it were not for the work of a German mathematician named Johannes Kepler. Kepler lived in Graz, Austria, during the tumultuous early 17th century. Due to religious and political difficulties common during that era, Kepler was banished from Graz on August 2, 1600. Fortunately, an opportunity to work as an assistant for the famous astronomer Tycho Brahe presented itself, and the young Kepler moved his family from Graz, 300 miles across the Danube River, to Brahe's home in Prague. Tycho Brahe is credited with the most accurate astronomical observations of his time and was impressed with the studies of Kepler during an earlier meeting. However, Brahe mistrusted Kepler, fearing that his bright young intern might eclipse him as the premier astronomer of his day. He therefore let Kepler see only part of his voluminous planetary data. He set Kepler the task of understanding the orbit of the planet Mars, the movement of which fit problematically into the universes described by Aristotle and Ptolemy. It is believed that part of the motivation for giving the Mars problem to Kepler was Brahe's hope that its difficulty would occupy Kepler while Brahe worked to perfect his own theory of the solar system, which was based on a geocentric model where the Earth is the center of the solar system. Based on this model, the planets Mercury, Venus, Mars, Jupiter, and Saturn all orbit the Sun, which in turn orbits the Earth. As it turned out, Kepler, unlike Brahe, believed firmly in the Copernican model of the solar system known as heliocentric, which correctly placed the Sun at its center. But the reason Mars' orbit was problematic was because the Copernican system incorrectly assumed the orbits of the planets to be circular. After much struggling, Kepler was forced to an eventual realization that the orbits of the planets are not circles, but were instead the elongated or flattened circles that geometers call ellipses. And the particular difficulties Brahe had with the movement of Mars were due to the fact that its orbit was the most elliptical of the planets for which Brahe had extensive data. Thus, in a twist of irony, Brahe unwittingly gave Kepler the very part of his data that would enable Kepler to formulate the correct theory of the solar system, banishing Brahe's own theory. Since the orbits of the planets are ellipses, let us review three basic properties of ellipses. The first property of an ellipse. An ellipse is defined by 2 points, each called a focus, and together called foci. The sum of the distances to the foci from any point on the ellipse is always a constant. The second property of an ellipse. The amount of flattening of the ellipse is called the eccentricity. The flatter the ellipse, the more eccentric it is. Each ellipse has an eccentricity with a value between 0, a circle, and 1, essentially a flat line, technically called a parabola. The third property of an ellipse. The longest axis of the ellipse is called the major axis, while the shortest axis is called the minor axis. Half of the major axis is termed a semi-major axis. Knowing then that the orbits of the planets are elliptical, Johannes Kepler formulated 3 laws of planetary motion, which accurately describe the motion of comets as well. Kepler's first law. Each planet's orbit about the Sun is an ellipse. The Sun's center is always located at one focus of the orbital ellipse. The Sun is at one focus. The planet follows the ellipse in its orbit, meaning that the planet-to-Sun distance is constantly changing as the planet goes around its orbit. Kepler's second law. The imaginary line joining a planet and the Sun sweeps equal areas of space during equal time intervals as the planet orbits. Basically, that planets do not move with constant speed along their orbits, rather their speed varies, so that the line joining the centers of the Sun and a planet sweeps out equal parts of an area in equal times. The point of nearest approach of the planet to the Sun is termed perihelion. The point of greatest separation is aphelion. Hence, by Kepler's second law, a planet is moving fastest when it is at perihelion and slowest at aphelion. Kepler's third law. The squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their orbits. Kepler's third law implies that the period for a planet to orbit the Sun increases rapidly with the radius of its orbit. Thus, we find that Mercury, the innermost planet, takes only 88 days to orbit the Sun, the Earth takes 365 days, while Saturn requires 10,759 days to do the same. Though Kepler hadn't known about gravitation when he came up with his 3 laws, they were instrumental in Isaac Newton deriving his theory of universal gravitation, which explains the unknown force behind Kepler's third law. Kepler and his theories were crucial in the better understanding of our solar system dynamics and is a springboard to newer theories that more accurately approximate our planetary orbits.
Okay, so that's the a nice little summary from from that NASA video. That there's a number of changes that Kepler makes to Copernicus's model that dramatically improves its accuracy. And so the most important one being the elliptical orbits. You've got to get rid of those perfectly circular orbits. You have to replace all the planet's orbits with ellipses. So the more elliptical an orbit is, you can describe that using the eccentricity, usually designated by a lowercase e. And so an object with an eccentricity of 0 is a perfect circle. If you have something that is 0.99999, close to 1, that's a very elongated, flattened ellipse. The closer you are to 1, the more eccentric, the more elliptical that orbit is. And it turns out that the Earth's orbit, for just as an example, is quite close to being a circle, but not exactly. And so that might seem kind of minor, but it's a major advance to give these orbits the correct shape, and that dramatically improves the accuracy of Copernicus's heliocentric model. And so it's really quite successful, and it gets rid of all of those weird epicycles from the Ptolemy's system, or model, I should say. So this is a big advance to that. Now, one thing that they mentioned in the video there, that a couple of nice terms here that we should be familiar with going forward. When a planet is closest to a star, that's a point called the perihelion. It's the closest point that it can be. And the opposite of the perihelion is an aphelion, and that's the furthest point. And the way I was taught to kind of tell these apart, these two words apart, is that perihelion is when you're close to something, aphelion is away. So perihelion is close, aphelion is away, and aphelion and away both start with letter A, and so that's how I was taught to remember it. And basically you can calculate the semi-major axis of a planet. Just add the two together, the perihelion distance and the aphelion distance, and divide by 2. Basically what we're saying here is that the semi-major axis of the orbit is just simply the average distance of that planet. And so for the Earth, we mentioned in our last session that the distance in miles between the Earth and the Sun is 93 million miles. So the semi-major axis of the Earth is 93 million miles. So that's all that semi-major axis really means. We're referring to the average distance from the star. The second law that was mentioned is just kind of a fancy way of saying that a planet is changing speed. This is the part where Kepler is abandoning this idea of uniform motion. When a planet is close to the Sun, it's moving rather quickly. When it is far out away from the Sun, it is moving much more slowly. And so that's what's happening as you get towards the perihelion. As you approach the close point, your planet is going to speed up. As it goes out away from the star and it reaches its furthest point, the aphelion, it's going to slow down. And so that's all they're saying. That's what the second law is about, that a planet is going to change speed depending on its distance from its star. And that's all it is. And this also is a big improvement to the accuracy of the heliocentric model. And Kepler's third law here, this is perhaps the most important of the three, because it actually allows us to calculate the period or the distance of a planet, depending on exactly what you want to do and what information you have. This is a very important equation. And so we should become familiar with it now because it'll come up throughout the course quite a few times. This is a very useful little equation, and it's fairly simple. And basically, the formula here is really quite simple. You have P is the period of the planet, how long it takes for that object to orbit around its star. So that's the P period. If you square that, it is equal to the semi-major axis squared. So in other words, the average distance of that planet or object, and cube it. And these two are equal to each other as long as we use the correct units. And so so this makes it rather nice. If you know what the average distance of an object is, you can use this to calculate what the period is, or the other way around, depending on what information you have. And so this is a very useful formula. And as I said, it's pretty important. It'll come up again throughout the course. And so I will give you an example of that at some point. I'll post an example on Blackboard of how you can do that calculation. All you need is a calculator. And so it's pretty easy to calculate that sort of thing. So these ideas that Kepler comes up with, they overturn more than 1,000 years of focus on this geocentric universe or solar system. And so this is a big advance, but at the moment, people don't really know very much about gravity quite yet. And this eventually will inspire Isaac Newton to come up with an idea of why this is happening. Kepler has discovered how the planets move, but he doesn't really know. No one at that point really knows why. No one really has a good handle on how gravity really works. And so that's where Isaac Newton comes in. And so not only does this idea of gravity apply to the planets, but it applies to everything that is around us. And so Newton comes along, and he is going to come up with an explanation of this. And of course, we can talk about Galileo. Galileo is really considered. We've already mentioned him and what he did with a telescope, but he was also known for his studies of motion, and he came up with this idea of inertia. And so he was doing actual experiments, dropping things, instead of just thinking about how gravity might work. He did actual experiments, and in this case, he found the tallest tower that he could find and dropped objects off the top of the tower and tried to measure how fast they were moving. And most people, I think, have the misconception that if you have something very heavy and something very light, if you drop it off of a tall tower, the heavy object is going to hit first. But Galileo found that that's not true. That a larger object, a more massive object, also has more inertia, a resistance to motion. And so it turns out that those things cancel out, and all objects fall at the same rate. So he could take two cannonballs, one more massive, much more massive than the other, drop them off the tower, and they would hit the ground basically at the same time. And so this is kind of counterintuitive, but that's really how it works. And in fact, when the Apollo astronauts landed on the moon, they did this as a kind of an interesting little experiment, sort of public experiment, to show that Galileo and Isaac Newton were exactly correct. And so here we see, I'll show this little video here of the Apollo astronaut with a hammer and a feather, and he's going to drop them on the surface of the moon.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
beautiful picture, Dave.
left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Superb.
And so there we go, a real life example of that in a vacuum. Two objects that are dropped, that get pulled down by gravity, but the two different masses will hit the surface at the same time. And so another thing that we should mention about gravity and acceleration is that they are what we call vector quantities. And that's a way of saying that not only do they have a magnitude, they also have a direction. And so, for example, acceleration, not only can it occur when your speed changes, your velocity changes, speeding up and slowing down are basic and common sense examples of acceleration, but you also get an acceleration when you change direction as well. And a good example of that is, let's say you're driving down the highway and you are on, let's say, an exit ramp for a highway, and you're going around a curve. So your speed may not be changing, but your direction is. And so you feel that. You feel that kind of motion where you get kind of pushed to the side as you go around the exit ramp. And so that is also the case. Not only can you get an acceleration from a change in speed, but you get an acceleration from a change in direction as well. Now, Isaac Newton, he wants to solve some of these problems with gravity. He'd like to come up with a mathematical way of describing gravity and what's happening. And in order to do that, he has to stop and invent calculus. So he does that and then comes up with three laws of motion. And in the end also discovers a universal law of gravitation as well. Now, we won't go into too much detail. I'm sure you've probably come across Newton's laws of motion in the past, so we won't really dwell on these. But we should review them just for completeness, I guess. The first law is the law of inertia. And, as mentioned, Galileo came up with this idea of inertia, but Isaac Newton kind of formalizes it a little bit. And so the first law of inertia is an object at rest will continue, or if it's in a state of uniform motion, it will continue that motion unless acted on by an outside force. So if an object is at rest and no forces act on it, it's going to remain at rest. That's perfectly common sense. But if you put a force onto that object, it will move as long as the force, the outside force, is acting on it. And so this is kind of a more or less common sense kind of law of motion. And an interesting idea, or one way of thinking about this, is imagine a bowling ball, and remember, or think about having a bowling alley that's extremely long and basically frictionless. And so if you take that bowling ball and throw it down this frictionless bowling alley, it will continue to go. And if it doesn't hit anything, it will just continue to move basically forever until some other force stops it. If there's no friction, it'll just keep going and going and going. And so that's kind of how a spacecraft will work. If you launch a spacecraft, you put enough force on it, it'll travel, and it'll continue until another force acts on it. Newton's second law is all about the mass and acceleration. And so he has this little formula here, F equals ma. F is the force, m is the mass, and a is the acceleration of that object. And so, think about a small car. Let's say a friend has a small car and you need someone to give him a push. You get out and you give it a push. If it's a small car, if it's fairly lightweight, sure, you could push on it and push it off to the side of the road if it's stalled or if he's having engine problems. But if your friend owns a large truck, there's no way that you're going to be able to apply enough force to accelerate that truck and push it off to the side of the road by yourself. And so that also is kind of a common sense type of law of motion. And so the third law is action and reaction. And it's usually stated this way: for every action, there's an equal and opposite reaction. And that's how a rocket works. You have this engine in this rocket. It fires off these gases, come shooting out the bottom of the rocket, and the result is there's a reaction to that force, and it propels the rocket up into space if you're moving fast enough. So that's kind of the basic idea of how a rocket works. And so that's the Newton's third law. Now, he also wants to come up with, as mentioned, a mathematical way of describing how gravity works, see how two objects can attract each other. And this is the formula that he comes up with, the law of universal gravitation. And it's usually written like this. And so you can calculate the force of gravity of an object by knowing what the masses of the two objects are and how far apart they are. And so this is what you see in this formula. F is the gravitational force. The two m's, m1 and m2, are the two masses of those two objects that are involved. And r is the distance between them. Plus, you'll notice there's a capital G, and this is the value. This is a constant that is part of the formula. And you might wonder, well, okay, that looks rather complicated. Where the heck did you get this from? Well, this all comes from experiments that have been done in the laboratory, watching how objects are affected by the force of gravity here on Earth. And so it's the value of G is known to very precisely. And so we can calculate that in the laboratory and use that in our formula here. And so this is the idea that Isaac Newton comes up with, is that gravity is not just a force, it's a force between two objects, not just one. So if you imagine the Earth and the Moon, the gravitational force between the two of them depends on the mass of the Earth and the mass of the Moon, not just one. The mass of the Earth, let's say. And the distance between them is what determines the gravitational force. And so you can calculate the force between the Earth and the Moon. And gravity is always an attractive force. It's always two objects attracting each other. It's never a repulsive force. And this applies to anything. Any two objects in the universe. And so that's why it's known as the universal law of gravitation. Now, if this looks kind of complicated, this is not a physics course. We're not going to be doing any heavy-duty calculations with this particular formula. But we should know how it works. And, as mentioned, you've got two masses here, and you have the distance between them. And notice the distance between them is squared. And so if you increase the distance between two objects, the gravitational force is going to go down rather quickly because you have this r squared, this distance squared. You're dividing by the distance squared. And so as the distance between two objects increase, the gravitational force is going to go way down. If it decreases, well, then it's going to increase the force by quite a bit. And so this is generally known as the inverse square law, because it is a square and it's, you're dividing by this square, and so it is known as the inverse square law. And this will come up again in one of the upcoming chapters about light, because the inverse square law can be used to describe how light travels as well. So here's just an example. If you look at this formula here without doing any heavy-duty calculation, let's say if you take r, the distance between these two objects, let's say the Earth and the Moon, if you double the distance, if you take 2 and plug it into this formula, well, remember r is squared, the distance is squared. So what is 2 squared? Plug it into your calculator, 2 and square it. Hit the exponent key, and you'll find that 2 squared is 4. And so now if you plug this into the equation, you're dividing by 4. So your force has gone down by a factor of 4. You're dividing by 4. And so the gravitational force, as I mentioned, gets weaker. And this inverse square law applies to light, electrical forces, and gravity as well. And so it's an important concept. We'll see it again in the upcoming chapter about light. Let's mention another example here. If you take one of the masses, let's say m1, and we double it, you're multiplying m1 by 2. Well, what happens to the force? Well, you've multiplied by 2, so the force goes up by a factor of 2. What if you double both of the masses, m1, m2, double those? Well, 2 times 2 is 4. So now you've increased the force between them. The gravitational force is multiplied by 4. What would happen? We talked about what would happen if you doubled the distance. What if you triple it? Well, what is 2 squared? 3 times 3 is 9. And so now you're dividing the force by 9, so it becomes much less. If you bring it 4 times closer, 4 squared, 4 times 4 is 16. Well, now you've increased the gravitational force by a factor of 16. And so this is, how this all works. It depends on the gravitational force depends on the mass of the object and the distance between them. And so hopefully this illustrates a little bit, without getting into too many details, how this works. And actually, we won't really use this for anything at the moment, but Isaac Newton kind of revises Kepler's third law, and he comes up with a slightly different formula. This is Kepler's third law is here, p squared equals a cubed, that describes the relationship between period and distance, and he revises it, putting the mass of those two objects, remember m1, m2, from his formula, gets added in there. And so we won't do anything with this at the moment, but this comes really handy later on when we start talking about planets orbiting around other stars, or when we talk about other stars orbiting each other. We can actually calculate the masses of some of these objects. And so this comes really handy for learning about other things in other solar systems out there. But we won't get into that right now. We'll see that pop up again later in the course. Now, speaking of masses, we should introduce this concept. I mentioned when we first talked about mass, numbers and mathematics in this course. There's a number of things we can do to make things a little bit more simpler. So, for example, if you want to calculate something about the gravitational force of the sun, you have to know its mass, and in this case, it's 2 times 10 to the 30th kilograms. That's an awfully big number to be dealing with. We can simplify this by coming up with a new unit that astronomers like to use, just simply called the solar mass, and usually written as 1 m sun. And so 1 solar mass, it really simplifies equations. You don't have to deal with that the scientific notation of 10 to the 30th. You can just use solar masses, and this will greatly simplify things later in the course when we start talking about stars. Okay, well, we're going to skip over this particular problem. As I said, this comes up later in the course. Okay, so we want to talk a little bit about orbits. We've already mentioned the elliptical orbits. The perihelion is the close approach of an object. Aphelion is away. That's the furthest point. And so that's distances refers to the orbits around the sun. But if you want to talk about something that orbits around the Earth, well, then we call that, is a similar word, perigee and apogee, G standing for Earth. And so perigee is the close point, and apogee is the furthest point of an object orbiting around the Earth. And you can apply these universal law of gravitation that Newton came up with and his laws of motion, and we can apply that to the planets, and we get some very accurate positions for the planets. And what do we find when we look at the orbits of these planets? Obviously, just as Kepler had suggested, the planets closer to the sun move faster. Planets that the planetary orbits have eccentricities, but they are small. So, for example, the Earth's orbit is very close to the circle, not exactly. It is an ellipse, but it's close. It has a relatively low eccentricity. Planets orbit all in the same plane and the same direction. That will come up again later when we talk about models of the solar system and try to figure out how solar systems came to be. This will be an interesting factoid that we need to add into our models. Orbits of comets and asteroids, however, are quite different. They're a little bit different than the major planets. And so here's a diagram of the solar system, or part of the solar system here, from Mercury out to Jupiter. And you can see the major planets are relatively circular, but some of these asteroids, the asteroids are shown in blue, have orbits that are a little bit different, and then you see the very elongated, very elliptical orbits of comets. Those are much more elliptical and tilted as well. And so these smaller bodies have a little bit of a different orbital characteristics here. Now, if you want to launch a spacecraft into orbit, the very first one was the Russian spacecraft Sputnik, launched in October of 1957. So if you want to launch something, you have to be launching it at the correct speed in order to get something out into orbit or get it away from the Earth. If you, for example, launch something with a velocity that is too slow, that is too small, you're not going to escape the gravitational pull of the Earth. And so here you see number 3, path number 3 here. This spacecraft is going to crash. It's probably going to crash back down into the ocean because it's not moving fast enough to escape the gravitational pull of the Earth. If you launch at a little bit of a faster speed, that's path 1, the yellow path. If you launch it a little bit faster, well, then that can get away from the gravitational pull of the Earth, but your spacecraft will enter a circular or almost circular orbit around the Earth, and so you'd get at least you would get your spacecraft into orbit around the Earth. But it doesn't escape the gravitational pull of the Earth entirely. If you want to do that, if you really want to send something away from the Earth out into the solar system, you need a much larger velocity, and that's the case here with path number 2. If you do launch it fast enough, it will escape away from the Earth if you're going fast enough. And so that's the idea here. If you want to get up into orbit, how fast is that? How fast of a speed do you have to go? To Earth orbit, it's 17,500 miles an hour. If you want to escape the Earth entirely, well, then you have to go significantly faster, at least 25,000 miles an hour. So you have to have a certain escape speed that you have to have in order to get away from the gravity of an object like the Earth. And so that's what these rockets are doing. And this is, as I mentioned, this is Isaac Newton's laws of motion here in action. Here's the action, and the reaction is the spacecraft goes up into orbit or out into space beyond the Earth. So we have some good examples of this. We have some interplanetary spacecraft that had achieved this escape velocity. And in some cases, we can use gravity to modify the orbit of a spacecraft or even give a little boost in speed. And that was the case with the Voyager 2 spacecraft. And it visited Jupiter, Saturn, Uranus, and Neptune. And it didn't, both the Voyager 1 and Voyager 2, they did not orbit around these planets. They were flyby missions. They flew past and went on to the next target. It didn't go into orbit, though we have sent other spacecraft that have orbited some of these planets as well. Flyby missions are relatively easy because it doesn't require that much energy. You're just kind of flying out there and zooming past, and so that's relatively easy to do. Or getting it to orbit around another planet, that's a little more difficult. It requires more fuel. And so here's a recent snapshot of the status of the Voyager missions, the 2 spacecraft. These were launched when I was a kid. They were launched in 1977, the fall of 1977, and they have been in space since that time. And so you can see the clock here, the mission clock, is over 45 years at this point. They've been in space for 45 years. It's really kind of incredible when you think about it. And so the current distance of the Voyager 1 and the Voyager 2 are the Voyager 1's almost 15 billion miles from the Sun, and Voyager 2 will soon be approaching 13 billion. So they are out there. They are way out there towards the edge of the solar system here. So if you want to launch a spacecraft like this, you've got to be moving pretty fast because not only have you escaped the gravitational pull of the Earth, you also need, if you want to go further, you have to reach the escape speed of the Sun. And that's what both of these spacecraft are doing. They are kind of leaving the solar system at this point. Now, the last section of this chapter, you'll be happy to know that we're skipping section 3.6. Because obviously there are more than just 2 objects in the universe. Isaac Newton's theory, or gravitational theory here, deals with the gravitational pull between 2 objects, let's say, the sun and the earth, or the earth and the moon. But obviously there are multiple objects in our solar system and many objects out there in the universe. And so it becomes a little more complex when you're dealing with more than two objects. And so there are little tricks that we can use to get around that. And you can use computers to calculate the forces between every pair of objects that needs to be calculated, but it gets really kind of awfully complex. And, this is not a physics course. We're not going to go into detail about this. Just, know that it's complicated and it can be done. And so we're going to be skipping 3.6 here. We'll skip 3.6 and move on from there. And so that is, in a nutshell, is gravity and orbits. And so I hope you found that useful. And if you have any questions about that, I'd be happy to answer any questions you might have. And as I mentioned, I will provide you with an example of Kepler's laws or Kepler's third law, how to calculate that. It's relatively simple. All you need is a calculator to do it. And so again, please feel free to ask me any questions about that.